And in this video, we're going to talk about two more types of conversions, not so much focusing on just going from moles to molecules, like pieces to larger pieces. We're going to use something that's actually really important because we need to be able to count out the number of atoms and the number of moles of a chemical that we're going to put into a reaction, but we can't physically go in and count individual pieces. So our way of doing that is by taking the object's mass. And so one of the things that we need is the ability to determine what's called the molar mass of an element or compound. And so that first term, molar mass, is the mass of 1 mole of an element or compound. Okay, and each element and each compound has its own unique mass associated with it. So thankfully, we've got this really great resource that's got, oh yeah, all these numbers here, these decimal values, we refer to those as atomic masses. All of those are already outlined for us, so nothing to memorize. We just need to know how to get the information and where and when to use it from the periodic table. Okay, so how do you calculate a molar mass? Using the periodic table, look up the atomic mass. We'll say atomic masses in the compound. If there are any subscripts next to an element, we're going to multiply the mass for that element by the subscript number. And then at the end, we're just going to add all the masses together. Pretty straightforward. I think once you see a couple of examples, you see it's kind of a simple process. Okay, so if we start with finding the molar mass of nitrogen, which is one of our 7 diatomic elements. Okay, nitrogen's one of the 7. We've got 2 nitrogens. And on the periodic table, we notice that a lot of these masses have got a lot of decimal, a lot of baggage after each one. We don't necessarily need all of that information. Some of these go all the way to 3, sometimes go to 4 decimal places. So what we're going to use is the atomic mass of each element rounded to the first 2 decimal places. So if you locate nitrogen on your periodic table, you can kind of see it on the screen here. Nitrogen's atomic mass is 14.007. So if we round that to 2 decimal places, we're going to call that 14.01. So 2 times 14.01. And because that's a mass, we're going to put the unit grams with that. But this is also referred to as a molar mass, so we're going to call that grams per mole. So if we have 2 times 14.01 grams per mole, our molar mass for all of nitrogen winds up being 28.02 grams per mole. Okay? So we've got another example problem here. This is nickel 3 nitrate. So we need to be able to count up how many nickel, how many nitrogen, how many oxygen atoms there are, equate the total masses, and then add them all up. So why don't you pause the video, try this practice problem out, and then resume to see how well you do. All right, so if we have 1 nickel, 3 nitrogen, and 9 oxygen. Remember that 3 distributes to each of the elements within it, and they each have their own individual subscripts. So it's like Ni with 3 NO3, so a total of 3 nitrogens and 9 oxygens. That means we need to find nickel on the periodic table, and it's got an atomic mass of 58.71. So this is now 1 times 58.71, which equals 58.71. We've got 3 nitrogens, which we found earlier, so 3 times 14.01, which is equal to, don't trust my mental math, 42.03. And then we've got 9 oxygens, and oxygen's kind of a nice round 16, 16.00. So that becomes 9 times 16.00. And 9 times 16.00 is equal to 144.00, keeping the 2 decimal places. Okay, so now the total sum for this whole thing We're going to add them all up. 58.71 plus 42.03 plus 144.00. We get 244.74 grams per mole. Now this number is one piece that we're going to use for the rest of our work. This tells me that if I wanted to have 1 mole of this compound, I need to mass out on a digital scale 244.74 grams. Or for nitrogen, if I wanted to have 1 mole of nitrogen, I need to get 28.02 grams of nitrogen. If I want 10 moles, I need 280 grams. So it's just kind of an equivalent ratio. Just like we did with the last set of notes, we're going to see how the molar mass can now also be used as one of our conversion factors. We can use 1 mole is equal to the molar mass of that substance. So in this first question, it says, how many moles of nitrogen are there in 42 grams of nitrogen? If we start with 42 grams, and now we want to start incorporating the formula in our work, using dimensional analysis, that's the label that we're going to carry down into the denominator. Okay, we already did the legwork for this problem. Up at the top, we found the molar mass. This is our ratio that we're going to use. So then that means that we can put 28.02 grams under 1 mole of nitrogen. Just like we did down here, 1 mole over the molar mass, because they're equal to each other, can be used as a conversion factor, or if we're going from moles to grams, we can use the other one. So now we got 42, remembering that these are all multiplied, 42 times 1, which we don't really have to do because anything times 1 is itself. So 42 times 1 divided by 28.02 to get our final answer. Now again, it's worth taking a little bit of time to say, well, 28 grams is what I need to have a mole. Do I have 28 grams? Yeah, I've got more than 28 grams. So I have enough to be equivalent to at least 1 mole. So then that means my final answer should be greater than 1. If I set all of this up and my final answer winds up being some kind of a decimal value, then logically I made a mistake somewhere. So 42 divided by 28.02 gives us 1.498. We're going to round that to a nice 1.5 moles of N2. And again, we want to get in the habit of canceling out our labels so that the only label that our final answer has is what's left over in the last numerator. Right? So if we do the reciprocal, another practice problem, now we're starting with moles and we want to go to grams. So I'm going to pause where you pause the video, practice writing this out. Remember that for this compound, we already did the legwork for the molar mass up here. Okay, so if we start with 1.3 moles of nickel 3 nitrate, that label, which is our starting value, is going to go in this denominator. So we're going to put MOL Ni NO3 3. And if we've got moles in the denominator and we're asked to go to grams, we know this fraction allows us to go from moles to grams in this fashion, because 1 mole, again, is equal to that mass of that compound. So 1 is going with the mole, and then the molar mass from up here, we're going to put in the numerator because that's the weight for 1 mole of nickel 3 nitrate. Okay? So now what we're going to do is cancel out our labels, moles cancel out, and then 1.3 times our molar mass is going to equal the total grams of that number of moles. Again, 1 mole weighs this much. We've got 1 and a little bit extra, so our mass should be at least this number and a little bit greater. Logically, we should have a number larger than 244.74. So we're going to multiply across. We'll say 1.3 times 244.74 is equal to 318.16 grams of nickel 3 nitrate. Okay? So 2 conversions we've talked about so far. This video going from grams to moles and moles to grams. In the last video, we talked about going from moles to molecules and molecules to moles. So it makes only sense that we should be able to take these two conversion factors and string them together to go from particles to mass and mass to particles. So these are now going to be a two-step conversion problem where we have two ratios that we're going to utilize in the same line of work. Okay? So this is saying what is the mass of 3 times 10 to the 23rd molecules of K3N or potassium nitride. We always start with our given problem, 3 times 10 to the 23rd MOLEC K3N. And again, that starting label we're going to put in the first denominator, MOLEC K3N. Now again, we've got these two equations that tell us we know 1 mole is equal to that Avogadro's number of particles, and the one we talked about just a minute ago, 1 mole is equal to the molar mass. It's also good to point out that on your periodic table, we've given you these equations so that you have them to reference as you go forward for your quizzes and tests within this semester. Okay, so we can only convert molecules to moles, and then if we want to get to grams, we need to know how many moles there are so that we can go from moles to mass. So that's why this requires two steps, because we got to use both equations. So in the first line of work, molecules here or particles can only go to moles. So we got to put 1 mole K3N in the numerator, and Avogadro's number I'm going to try and fit down here in the denominator. Okay, so now molecules K3N will cancel. The only label we have left over is moles. So in the next multiplier, remember these are all multiplied together, we're going to put moles in the denominator, and then we can go from moles to a mass in grams in the numerator. So 1 mole is equal to the molar mass, and this is where we have to take a little bit of time to figure out what's the molar mass of K3N. So we have 3 potassiums, 1 nitrogen, and so if we get out our periodic table again, we look over here and we see that potassium has a mass of 39.10. Nitrogen has a mass of 14.01, 2 decimal places. So we need to simplify those. 39.1 times 3 is equal to 117.30. And then 1 times 14.01 is just 14.01. And so this sum, the molar mass of that compound, we're going to put in the last spot of our work. So plus 14.01, the molar mass of K3N is equal to 131.31. And then lastly, we can now cancel out moles, K3N, and this now lineup of work allows us to convert molecules to moles to grams without having to do two individual proportions. Okay, so again, we got to be careful because we've got scientific notation. So in our calculators, we want to use parentheses. We're going to say 3EE23 divided by 6.02 EE23 times 131.31. And we get a final answer of 65.4. Okay. So in the last example, we're now starting with a mass, and we're trying to go from mass through moles to molecules. So again, pause the video, give it a shot, and we'll see how you do. All right, so if we start with 45.6 grams of O2, our first conversion factor that we're going to multiply by is to get grams canceled out. So we're going to put grams O2 in the bottom, and we can go from mass only to moles. So we're going to put 1 mole O2 in the numerator, and this is where we need to do, again, the molar mass of oxygen. So oxygen's atomic mass is 16.00. We've got 2 oxygens, so 2 times 16.00 is equal to 32. 0.00. So there's 32 grams equivalent to 1 mole. We've got more than 32 grams, so we definitely have a mole. And then we want to go all the way to molecules. So in the next conversion factor, now that grams O2 have canceled, we can line up and put moles O2 in the denominator, and we know that 1 mole of anything is equivalent to 6.02 times 10 to the 23rd molecules of O2. So now moles will cancel, and our work is now lined up accordingly so that our labels cancel out, and it shows us the math that we need to follow. 45.6 divided by 32 times Avogadro's number, 6.02 times 10 to the 23rd. So in our calculator, we'll start with the division and then multiply with parentheses by Avogadro's number, and we get 8.6 times 10 to the 23rd molecules of O2. So the image that I ended this page with that you see on your screen is something that we call the mole roadmap. The only reason I use that is sometimes it's a nice visual to show you the number of steps that you need. If you are given a number of moles of an element or compound, we can convert in one step to get to the number of particles, or we can convert in one step to get to the number of grams. Okay? So if we start at moles and we want to go to grams, we know we're going to use the molar mass over 1 mole. And then if we start at moles and we want to go to particles, we're going to use Avogadro's number over 1 mole. And then the opposite of those fractions are true. If we want to go from particles to moles, we would have to use 1 mole over Avogadro's number. And if we want to go from mass of an element or compound back to moles, we would have to use 1 mole over the molar mass. The true purpose of this whole thing is that if you're at grams, you have to go to moles first, and then you have to go to particles. There is no connection that allows us to convert the number of grams of an element or compound and then equate it directly to particles. And there's no way we can be given a number of particles and then convert in one step directly to mass. Okay, so there has to be that equivalence of given Avogadro's number, how many moles is there? And then given that number of moles, how many grams is that? Okay, so it'll help you kind of visualize. If you start with grams and you're asked to go to moles, it's a one-step conversion problem. But if you're given particles and you have to go to grams, it requires 2 steps, 2 conversion factors to get that problem done.